saints in lockstep.
Hello and welcome to the concepts video on double angle identities. So first off, I'm just going to present what they are. So here's the first double angle identity that we could have. Let's say we have sine of 2 alpha, where alpha is an angle that we know or something like that, some angle. And we're taking sine of double that angle. Okay, hence the name double angle identities. This is going to be equal to 2 times sine of that angle alpha times cosine of that angle alpha. Okay? Alrighty, so that's the first one. It's pretty straightforward. That's basically all there is to it. And now let's go over a second double angle identity. So this is going to be cosine. Okay, so cosine of 2 alpha is equal to, and this is going to be cosine squared of alpha minus sine squared of alpha. Okay, so this is kind of like, I'll say this is option A for kind of rephrasing cosine to theta, or to alpha. Okay, because using the Pythagorean identity, we can, so let me just write a little side note here. So because of the Pythagorean identity, which is cosine squared alpha plus sine squared alpha is equal to 1, we can actually replace some of these things and just make it look a little bit different, this equality here. Okay, so we could say, for example, cosine squared alpha is equal to 1 minus sine squared alpha. And because of that, we can plug in this right side into our cosine squared alpha. So form B of identity number 2 could be cosine of 2 alpha is equal to, and now for the cosine squared, I'm going to plug in 1 minus sine squared alpha minus another sine squared alpha from the identity there. So this will just turn into 1 minus 2 sine squared alpha. Okay, so this is like kind of just version B of identity number 2. We could also do it the other way as well. So let's go back to our Pythagorean identity. Let's say we solve for sine by itself. Sine squared alpha is equal to 1 minus cosine squared alpha. So that means now we could actually just plug in this 1 minus cosine squared alpha into the sine squared part from version A. I know this is a little bit confusing. I'm just kind of introducing the different forms of identity number 2 that you could see. So this is the first one. Let me just box that there so you don't lose track of it. Here's the first version. Here's version B. Cosine 2 alpha is equal to this guy. And now let's work with version number C here, or version C. So cosine 2 alpha is equal to cosine squared alpha, and then minus, and in for this sine squared, I'm going to plug in 1 minus cosine squared alpha. Okay, so this is going to be equal to a 2 cosine squared alpha, and then minus a 1. Okay, so here is version number C of that same identity that we were using from the beginning. Okay, alrighty, so there's this one. This is just identity number 2. So they're basically 3 different ways. Okay, so one way to rewrite sine of 2 alpha, and there are 3 ways to rewrite cosine of 2 alpha. Okay, so those are just the 3 ways laid out there. Okay, so here's an example in which we would use our double angle formulas or identities. So let's say we're given that sine theta is equal to 3 over 5, and theta is in the second quadrant. We're going to find exact values for sine of 2 theta and cosine of 2 theta. Okay, so let's draw out what we have. So we have some circle, right? Our unit circle. Theta is in the second quadrant, somewhere over here. Okay. Sorry, those are just really bad lines right there. Okay, so theta is here somewhere. So we could say, well, let's just draw a triangle. Let's say we have, here's theta, right? And then sine is opposite over hypotenuse, so this would be 3 and this would be 5. So we have that sine theta is equal to 3 over 5. And we have that cosine theta should be equal to, well, this is a 3, 4, 5 triangle. This isn't to scale, by the way. But anyways, we have cosine should be adjacent over hypotenuse, so that would be 4 over 5. 4 over 5. And since cosine is, that represents our x value, and x is negative in the second quadrant, we should also have a negative sign in front there. Okay, so we just solved for simple sine, which we were given, and we just solved for cosine, just in case we need it to figure out sine of 2 theta and cosine of 2 theta. So let's write down what we know. So sine of 2 theta, according to our double angle identity, should be equal to 2 times sine theta times cosine theta, which is good because we know both of those values now. So 2 times 3 over 5 times negative 4 over 5. So this is going to equal a negative 24 over 25. Okay? And we're done with that. Check mark there. And now let's see cosine of 2 theta. Okay, so this is the one where we have 3 different forms that we could possibly use. In this case, I'll just pick the, I don't know, option B it was or something like that. I don't really remember which ones. But anyway, so 1 minus 2 sine squared theta. And the reason for that is just because we were given sine theta in the beginning, so we might as well just use the one that just requires the information that we already have. So 1 minus 2 times sine squared would be 3 over 5 squared. Okay, so this is equal to 1 minus 2 times 9 over 25. So this is like 1 minus 18 over 25. And this is going to end up being a positive 7 over 25. Okay, and that's cosine of 2 theta. We can also use double angle identities to simplify expressions such as these, even though this does look pretty simple already, but it could be even more simplified, okay? By saying that, well, the top, one of the versions that we could write this as is cosine squared t minus sine squared t, right? That was version like A or something. On the bottom, we just have that thing that was already there, okay? The top can actually be factored because that's a difference of squares, right? So we have cosine t plus sine of t times cosine t minus sine t. That's all on the top, and on the bottom we have this cosine t minus sine t, which actually very conveniently cancels with the one on the top, right? So we get that this actually simplifies whatever we had in the beginning to just simply cosine of t plus sine of t. And that's pretty much as simple as it gets.